This is a video for MEI Core Pure Mathematics, Hyperbolic Functions 2, Inverse Hyperbolic Functions, 2.2, Differentiating Inverse Hyperbolic Functions. If we want to find the derivative of r sin x, so this thing here, d by dx of r sin x, we start by considering y equals r sin x. Now remember that you might see this written as sinh to the minus 1. Either way, we mean the inverse of sinh. So if y is r sin x, then sinh y is equal to x. And if I now differentiate this with respect to x, I'll get cos y, dy by dx, because we're differentiating implicitly, is equal to 1. Remember, if I differentiate sinh, I just get cos. Rewriting this then, I'll get dy by dx is equal to 1 over cos y. And we know that cos squared minus sinh squared is equal to 1. So if I rearrange this, I'll get cos squared equals 1 plus sinh squared. So this is going to be 1 over the square root of 1 plus sinh squared y. And I need plus or minus here because I've taken a square root. Now if we look up here, I can bring this down into here and rewrite this to give me dy by dx is equal to 1 over the square root of 1 plus x squared. And what about the plus or minus that we've got here? Well, if you think back to the graphs that we've seen in a previous video, we know that the gradient is always positive for r sin x, so we only take the positive square root as in here. There's that written up a little bit more neatly. This is where we use the inverse sinh to give me this, the implicit differentiation and rearrangement here, and then this is where we've used the fact that cos squared minus sinh squared is equal to 1, and then we've used this fact down in here to give us the final result, along with the fact that dy by dx is positive, so that we can get rid of the plus or minus and just take the positive square root. Now there is an alternative way of doing this. You could use the fact that r sin x is this in logarithmic form, and then you could differentiate that using the chain rule. Be careful when you're doing that because, of course, you've got a square root in here. Remember to use power a half, so I would rewrite this as log of x plus x squared plus 1 to the half, and that just makes the differentiation of that a little bit easier to handle because you've got the powers in there already. Remember, this is a chain rule type differentiation, so you're going to get 1 over this lot multiplied by the derivative of what's inside the log. And you could work that through for yourself and see if you get the same result as we got on the previous slide. So what about differentiating our Kaushiks? Well, it's exactly the same technique. Here we've switched the function round, so we've got cos y equals x, the implicit differentiation and rearrangement. And again, we've used this cos squared minus sinh squared is equal to 1. And then at the bottom here, we've again used the fact that we can back substitute to get an x into there. And again, we've used the fact that the gradient of our Kaushiks is also positive. So those are our two results that you need to know about. It's useful if you can remember them, but they are in the formula book, so you can quote them straight off. You don't need to derive them every time you use them. You can just quote them. So how would we use this? Well, let's look at differentiating r sin 4x. So I want d by dx of r sin 4x. And this is a chain rule type differentiation. So I'm going to get a multiply by the derivative of 4x in here as well. So it's going to be 4 times the derivative of r sin x. Now my x thing is 4x, so I'm going to get 1 over the square root of 1 plus 4x squared, and then times the derivative, which is just times 4, the derivative of 4x. And this then tidies up to 4 over the square root of 1 plus 16x squared. And there's the neater version of that, and you can see it's exactly what we had on the previous slide. And so the summary of this then, you can differentiate r sin x, you get this, and you can just quote these results. Remember, they are in the formula book. And if you differentiate r cos x, you get this. And we'll use both these results in a later video when we start to look at integration using inverse hyperbolic functions. The next video in this sequence is 2.3, integration using inverse hyperbolic functions.